Hello everyone, welcome to another NPTEL lecture on isotope geochemistry. Today we will discuss about isotope dilution. This is a technique where you can measure concentration of an element and isotopic ratios together in a given aliquot. Now in the previous lecture we saw how mass spectrometer is used to measure isotopic ratios very precisely, but this cannot be used to measure concentrations also. For that reason you need to add a tracer to get the concentration data for the same aliquot. Additionally, when you are doing stable isotopic measurement, you need to have a stable isotopic ratio for mass fractionation corrections or the instrumental corrections, which is often not available for stable isotope, because we are assuming all the isotopic ratios can fractionate. In that case, you need to add an external tracer which can be tracked for these instrumental corrections. For this reason, isotope dilution is very critical for concentration measurement and also instrumental fractionation corrections for stable isotopy measurement. Let us discuss more about this technique. Before I go ahead, I will just quickly go through what we discussed about mass spectrometer. We discussed that mass spectrometer have three components. One is a source, one is an analyzer, and third important part is detector. Now in the source part, when you have a particular element, you can ionize it and you can accelerate it by giving an electric potential, and then subsequently once it reaches to the analyzer part, if it is a magnetic sector, then it will get a centripetal force and they will disperse in different radius. Depending on their E by M ratio, they will follow different radius, and you can measure different isotopes using multiple detectors. When you do this, there is something called the total efficiency of a mass spectrometer. What does this include? It includes what is the ionization efficiency of the instrument. That means, if I am loading 100 atoms of an element, how much of it is getting ionized. So, let us say you have loaded 100 atoms, only 1 to 5 atoms get ionized. So, this efficiency of ionization is typically about 1 to 5%. After they get ionized, transmission efficiency, the electric filters that are there, they will ensure that you get a good signal in the detector, but at the same time it will restrict some other ionized particles to reach to the detector, and hence you will have a difference in what got ionized and how much it ultimately reached to the detector. And third is the detection efficiency. So, amount of ions that is reaching the detector, how much of it is counted by the instrument, is all included to tell you the efficiency of a mass spectrometer. Often the detection efficiency is about 100%, but we do not have a control on ionization efficiency and transmission efficiency. If you do not know these two terms, then we cannot calculate back what is the concentration or how much strontium is loaded at the beginning, which is an indicator of the concentration. But sometime prior to this purification process, where you are doing column chemistry, means you have a rock, that rock goes through a column chemistry to get pure strontium, and this column chemistry is also not 100%, it varies from 60 to 80%, and for that reason there is no way you can track back the amount of strontium that was there in the rock or whatever samples you processed, and hence you need to add a tracer to find the concentration. And that is where isotope dilution becomes important. In isotope dilution, what we do, let us say we have a rock sample, we are interested in measuring a particular isotope, let us say strontium, 87 strontium by 86 strontium. So, what you will do, you will take the rock, dissolve, then do a column chemistry, then you will get the pure strontium that will go through mass spectrometer, and ultimately you will get the required 87 strontium by 86 strontium. Now, in case of isotope dilution, what we will do, we will add a tracer or spike, and rather than dealing with the rock, now we will deal with a mixture, and the same process will be followed, where you will measure 87 by 86 strontium, but this is not for your sample now, it is for the mixture. And doing some mass balance calculation, you will get the concentration data, even you will be able to extract the 87 strontium by 86 strontium value for the particular sample. The tracer or spike is nothing but a solution which is enriched in a particular isotope. Solution which is enriched in a particular isotope. What that mean? So, if you take a natural sample for strontium, you will have 84, you will have 85, 86, 87, 88. So, in case of strontium, 84 is very small, 85 is less, 86 is around 10%, 87 is about 7%, 88 is around 84%. So, this is the natural signature. You will add a spike which is enriched in a particular isotope. Generally, those isotopes are created in a cyclotron, where strategically the lowermost isotope, in this case 84 is the least abundant isotope, is enriched, and the other isotopes are actually negligible. So, it is a 84 enriched, 84 strontium enriched spike is used, so that you will create a mixture of the sample and the spike and do mass balance calculation to find the concentration and 87 strontium by 86 strontium. I will derive the mass balance calculation for the mixture, and also will give you an example how this can be used to find concentration in a real time data. What we are discussing right now is, you have a sample which is often have a natural isotopic abundances, and you will have a spike. This spike is enriched in a given isotope, and a mixture is created, and you are measuring isotopy ratio, let us say Rm, which is A by B. A is one isotope, B is another, like 87 strontium is A here, 86 strontium is B here. In that case, Rm can be written as, which is A by B for us, will have natural A plus spike A in atoms divided by natural B plus spike B. So, if you are representing them in atoms, then isotopic ratio is nothing but the amount of A coming from natural or your sample plus spike. Let us say the abundance of A in natural sample into number of moles of N plus abundance of A in your spike into total amount of the element that is there from spike divided by N into A B B N plus S into A B B S. Let us rearrange this. So, if you do this R M N abundance B N plus R M S A B B S is equal to N A B A N plus S into A B A S. If I take N common, this is R M abundance B N minus there is another term of N here A B A N is equal to S into A B S minus R M S A B B S. This is what we derived in the previous page. Now, let us replace N, which is in number of atoms actually. If you translate that into gram, then we need to bring in the atomic weight, which is Wn for the natural ones. This is the atomic weight, and A is the Avogadro number. Similarly, S is SW. SW is the amount of spike that you have in grams multiplied by A into Ws. So, this is atomic weight. This is atomic weight for spike. This is atomic weight for natural samples. If we replace this N here, this is Nw into A by Wn is equal to Sw into A divided by Ws A B A S minus R M A B B S divided by R M A B B N minus A B A N. So, if you cancel out the A and rearrange a bit, then your Nw can be is equal to, then Nw is equal to Sw into Wn by Ws A B A S minus R M A B B S divided by R M A B B N minus A B A N. So, if you want to calculate how much gram of your sample is there, how much gram of an element is there in a particular sample, and if you know how much gram of spike is added, of course, when you do the analysis, you keep a note of how much spike is being added. This is atomic weight of the natural sample for rubidium or for strontium, whatever element you are analyzing. This is atomic weight of the spike. Abundance of A in spike is often known, abundance of B in spike is known, abundance of A and B is also known. The only thing that you need to measure is Rm, the ratio of the mixture, isotopy ratio, which you can measure. If you can do that, then you get the isotopy ratio by mass spectrometer analysis, and the same analysis can be used to find the concentration, and this is how isotope dilution works. The success of isotope dilution to give you very precise and accurate concentration data and isotopic data, what we need to know is we must have a precise information on the concentration and isotopic abundance of the tracer. The spike that you are adding, we must know the exact concentration and isotopic abundance of that spike. Often you can calibrate these concentration and isotopic informations before your isotope dilution measurement is being correct. The isotope dilution measurement is being conducted. After that, when you are doing the sample and spike mixture preparation, you must ensure in room temperature or by heating in a closed chamber, you must ensure that the sample spike are well equilibrated in this mixer. If they are not isotopically equilibrated, then you may not find precise number, and often that happens when the oxidation state of the element are different for sample and spike. So, while you are conducting the experiment, you must ensure that the mixer is in isotopic equilibration in terms of the sample and spike mixing. Additionally, you need to know how much spike you must add in a given sample. If you are adding less, then it became under spiked. If you add very large amount of spike, then this became over spiked, and hence you must add spike in a given amount of sample so that you get the least error during the measurement. So, this is the zone where you can find the very precise measurement, and to do that you must create the mixer in such a way that its ultimate isotopic ratio is a geometric mean. So, it must be the Rm must be equal to Rn plus Rs. So, if you know the natural isotopic ratio and isotopic ratio of the spike, then you must target to add exact amount of spike where this isotopic ratio is closer to this value. If that happens, then you are going to fall in this value zone of less error. Second is, your measurement can introduce large error if the element purity in the spike is not very good. So, that also can control the error in your concentration measurement. When you are dealing with not single spike but double spike, the double spike is needed when you are interested not only on the concentration but to find a stable ratio for your instrumental fractionation correction. In that case, the two you will add not one spike, you will add two spikes, they are called double spike. So, in that case, the proportion of these two isotopes must be added in a such a way that the double spike does not introduce large uncertainty. Now, I will take you through an example of rubidium concentration measurement using isotope dilution. This particular measurement is done by adding a spike which is enriched in 87 rubidium. So, the abundance of rubidium 87 and rubidium 85 in natural and spike samples are given. So, you know the natural abundance and you know the spike abundance for two naturally occurring isotopes of rubidium, which are 85 and 87. Now, what is done here, that you took 0.25 gram of your sample and dissolved it and created a solution of 50 ml. In that you added a spike, and the spike abundance of course is given, this is the isotopic abundance. So, this spike actually comes from a solution of spike solution, and this has a concentration of 7.5 microgram per gram of rubidium. So, this is the concentration of rubidium of the spike solution. From this you took 3.5 gram and added here. So, this means 3.5 gram of spike with a rubidium concentration 7.5 microgram per gram is added. So, now you created a solution, and that mixture give you an isotopy ratio of 87 rubidium by 85 rubidium of 1.55. With this given information, you need to compute what is the rubidium concentration for this rock sample. Let us try this. So, this is the expression that we derived. N weight means the amount of rubidium that is there, rubidium in grams that is there in rock, is equal to how much gram of rubidium added in the mixer. Atomic weight of natural sample and spike I have calculated, it is given in this table. Abundance of 87 spike is given, abundance of 85 in the spike given. This is the mixer number which is given, it is 1.55. This is known, this is natural isotopy ratios known. So, if you put all these numbers here, the final number that you get is 30.25 microgram. That means, in the 0.25 gram of the sample, independent of whether you diluted to 50 ml or 25 ml, this 0.25 gram of rock contains this much microgram of rubidium. Then the total rubidium concentration becomes 30.25 divided by 0.25 gram of rock is 121 microgram per gram. So, this is how you compute concentration of element using isotope dilution technique. This is a very strong technique that is often being used in solid source mass spectrometer. I want you to go through Gunter Fore book again, the second edition. There are some numericals, please try them, and I hope this will help you clarify all conceptual understanding about this wonderful topic on isotope dilution.